Next guest is Aayush Bansal. He has done his PhD in robotics from Carnegie Mellon University, where Simon Newell pioneered AI. Post that, he went to work for Meta Reality Labs, where JEPA is being developed. And very recently, he's exploring 4D world models for real world problems. And he's working in India in a dense, complex environment. So I thought it makes sense to chat with Ayush and learn and understand more about world models. Hi Ayush, welcome to my video chat series.
Thank you, Kalyani. It's nice to talk to you. Looking forward to all your questions that you have. Let's dive in.
Everyone's starting to say now that LLMs are a dead end and you need world models to do real AGI. What is AGI? Also, no one's ever agreed to a definition of AGI. I wanted to get your views on this first.
Okay. So where should we start from? LLMs are dead end. So I think we need to calibrate our expectation first. So LLMs are good tools, right? Now how should I define this thing? Let me think of something. So there are three questions over here. LLMs are dead end. The second thing is everyone started to talk about the world models, and then the third thing you asked is about AGI, artificial general intelligence. Okay,
Yeah.
so let me try to give in my honest answers about each of them. So honestly, everyone has their own version of AGI, artificial general intelligence, as what they say. And I honestly don't know what it means. And it is a true condition for most of the people I know. I keep asking them, what is it that people mean when they say AGI? And they don't really have any concrete answer basically for that. But my understanding is let's say you want to build like a system which can adapt in a environment like we humans. So up till now, how is it that we have been building robots? We would say that, okay, this is a particular task, and let's say we need to mop the ground floor. So here goes Roomba. We need to have a chef or a butler. Some other robot comes in. We need this thing, that thing. So if you think from that perspective, even for just doing simple home task, you will build a place where you are keeping 100 robots, right? That's too much to ask for. Can we have one robot which can do all of these tasks one at a time? Like somebody who can clean the thing as well, can clean your shelf also, can arrange it nicely, can make sure your living room is nicely packed, can do your laundry as well, and can take it out and iron your garment. Just one system which is doing all of it. Think of it like this way: uh, a good human. It's not something that you have to bake into like a machine to say that you should be able to only work in this particular environment. Like human, they would be able to evolve in the new environment they are being kept. Okay. So think of it this way. If I go in a new apartment, right? I can set it up the apartment from the things that I have. I can mop my floor. I can do the dishes. I can do my laundry and also know where to hang it if I have to do it in sun or something like that. Or if I have to iron my clothes, I know all of the things that I can do in my apartment. Can we have a computing equivalent of that? Or maybe say a non-biological equivalent of that, which can do without much instructions. Like goes in a new environment and be able to do all of these tasks.
But we have that now, no? The humanoids.
No, but what is it that those humanoids are able to do? That's a question, right? But the humanoids that we have can do very limited tasks. I mean, might be thinking of the cool videos that we see on internet doing all the backflips and all those things. But
Yeah.
the truth is, the things which looks fancy are easier for a humanoid to do. The things which look easy are very challenging. So if you just say like hold certain thing with a particular precision and all of those things, that's just challenging. So at most of the time, I mean, how many times you do backflip in your regular day? Or I don't know any of those stuffs, right?
Yeah.
It's the basic stuff that we need our help with. So I haven't seen any of such systems which can do a general purpose robotics like hell. Even though we have some hardware humanoids, and the truth about the humanoids that we have built some good demos, but real world is way too far ahead from the demos. So this is what I think or long answer for AGI. Okay. Then let me see, let's say the LLM part now. LLM and the dead end of LLM. Okay. And how is it that we are seeing all of these success in LLM? Okay, LLM, as we know, large language models, which have seen a lot of success in the recent past. People would ask them certain thing and they are able to produce a document and very well written statements and everything, right? And so we see that, okay, there is some structure which is coming out. First, why is it happening? Partly because the language that we see is a very structured space, right? Each language has its grammar and the set of rules that exist, right? So we have good machines which can understand the pattern in the languages and be able to predict, okay, these are the things which the human user might be interested in. So churned a lot of data, scraped a lot of data, and be able to provide all that information. But does having a LLM or large language model, is it a sign of intelligence? I personally believe it is not a sign of intelligence. Then you may ask, what is actually intelligence? Right? So there is a difference between knowledge and intelligence. First, I would say just knowing a particular language is not a sign of intelligence. There are biological beings other than humans also, which are quite intelligent in the task that is needed. For example, an ant, okay, a mice, or even a bee who knows how to navigate its path, who knows where to go from point A to point B without any navigation, right? So these are biological beings which are intelligent. They don't have any specific language or something like, or at least we don't know about the language, and yet they are able to do their work. So I would place them in an intelligent thing. Right now, what we have with LLMs is a very big machinery which is able to understand the structure in the language that we have. Okay. And because of the nature of the large amount of data that we have trained on, we are able to extract like, okay, and there is exists a structure in the language. Once again, we're able to get the output. Now one may say that LLMs have advanced a lot, which is right, because like because of the big machinery and lot of data that goes into it. Like let's say you have your data from say Shakespeare and J.R. Tolkien and all your favorite authors, right? And you also have like let's say all the important exams in the world, say accountancy or legal and all those things. Now the question that we should ask is it a knowledge test or is it an intelligence test? So in my understanding, most of the time that we are doing is a test for the knowledge. It's not a test for an intelligence, right? So yes, LLMs are a good knowledge machines, which if you ask them a specific set of tasks which already existed, they can tell you. But if you create a new task, that's very challenging for them to do. So now why? So this is LLMs. Okay. So I would say LLMs as knowledge stack, not intelligence. Okay. And they are good machines to understand the structure in the language which exists, right? Everyone would agree, like even you don't really need any technically uh, a person with a technical understanding, they know that there's a structure in the language,
Yeah.
grammar, and all of those things are structure. LLMs learned all of that, right? Because they have been trained on large amount of data. Okay. Now, are LLMs dead end? Okay. Uh, so I don't know the answer, dead end. But what I know is, in my understanding, this is what like if there is a structure in something and it needs to be conveyed in some sort of a language, that is what I would use LLMs for.
Yeah, but I'm asking dead end because is there an evolution from here, from where we are today, after all the innovation that's happened, all the research that happened on LLM? Do we need to move to the next thing, or is there more potential here beyond what you're just saying, using it for knowledge work?
So okay, let's see. Let's try to delve into this space. What is it that we need for a truly intelligent machine? I don't know the answer, but let's
Yeah,
try
yeah,
to
we are
do
brainstorm.
let's try to do the reasoning over here. Okay. Say, and one of the things I really liked about like let's say the Indian ecosystem is a completely unstructured environment, especially in various things. Say on the roads or now, can you just point your camera on the road and ask about the navigation? It's very challenging because lane markings are not there. The signs are not there. Traffic signs are not there properly, right? So can we have a system which can operate reliably in these kind of unstructured environment? We don't really have a system that can survive in this particular unstructured environment. So the question comes, does the machinery that we have learned for modeling the language can operate in unstructured environments where things change drastically? They don't really remain same every day. They don't really say remain same over the period of a day as well, right? And the answer is no. And if you start taking a lot of such domains, like let's say from the robotic scenario also, I think the answer would be yes. But This is where LLMs comes in handy. And once again, I think LLMs are good language tools. We have become quite nuanced in explaining language is a way to communicate. It's a very compressed form of communication. Like to do simple tasks, it's a very good tool to communicate with an individual.
Them as dead ends, and you said कि हाँ उनका एक potential है and there are use cases for it, but we need to also.
So okay. Uh, LLM's language. Okay. Language as a good way to do communication, right? It's a compressed form of communication, meaning like if I have to tell you about the beauty of certain things, it's definitely not the right thing to do, right? But if I have to do some daily instructions, it's a very good way to do it, right? So yes, robot can understand language, human can understand language. There can be an interfacing that can exist. But then there comes an important things also like performing tasks or activities or understanding those tasks and activities. LLMs are not there. And I don't really see a way LLMs can go over there. You would need to understand the world beyond the language. You need to see, hear, touch, all of those things that gives the special power to biological beings is needed for the intelligence to emerge. I mean, think of it this way: even in our own, like this is a perfect, like human body is a perfect engineering example, right? Like a great biological being. I mean, they're better also, but let's say, but over here, is it just what we speak or the language? Is it that does that make us intelligent? No, there's so much reflexes, sense, perception, senses, hearing,
Yeah,
touch, and all of those things that are needed to make observation and inference
correct.
on a daily basis that we don't even understand, that we don't even realize.
Yeah, vision is a very critical part of that intelligence.
Vision, touch, right? Hearing. There are so many things happening within the reflexes also that we don't even know how to name them, those senses.
Got it. But then how is human, I know we spoke about this, human able to handle so much context, complexity at a power that's, I don't know, like 20 watts or something versus this, the whole AI world is trying to just compute problem. And I'm like, imagine someone thinking top down that कि मैंने humans बनाया मुझे इतना natural resources लगेगा to get them to function. That's not how it works, right? If we were to replicate human like intelligence, compute has to be solved. You cannot never ending keep creating compute. So like, what's your thought on that?
So what I think is we are right now in a research phase.
It should not be now we got a new technology, build more data centers. So I'm saying,
Yeah, that's not reasonable way to go actually. I'm totally against that particular thought process. The thing which I can say is, as a scientific expedition to set up a gold standard, you can say that I'm going to use all the resources and be able to get the best possible performance. Okay. But once you have done that scientific expedition, you can't say I'm just going to remain on that scientific expedition and keep using all those resources for my daily life. That's a sheer misuse of
yeah,
resources. Like, I mean, I can give you an example. So, for example, the reality labs at Meta, right? They build these studios with like 500 cameras and all of those things, right? To build human body avatars or facial models and all those things. It's a good expedition to say that this is the quality of the results I aspire for.
right.
Would you want to bring in a billion people over there in those studios to do the scanning? It's not scalable and it's not the right thing to be doing. The right thing to be doing is to use your mobile phone, right? For once, just to say that I want to challenge myself and get this quality of results to set the gold standards. Let me use the maximal possible resources that I can use as a scientific expedition. But once you have done the scientific expedition and set up like, okay, these are the standards which I'm gonna aspire for, you're gonna commit to very minimal resource setup and say that let's try to solve the problem with the minimal resources.
I have a follow up on that, but for that, we need to introduce the audience to world models. So, let's do the evolution of world models. Where did it start from? What were they trying to solve? The equivalent of Alan Kay and everyone in that times period when PAC was getting developed and all. What were they thinking of?
So if I have to put it naively, and different people have their different interpretation, okay? And let me say it naively. What is my understanding of world models? World models are like the mental model. Say when you wake up, you have an understanding of the space and the environment you are, right? And how you can do certain tasks or set up things to to be successful in that environment, or to survive in that environment, or to thrive in that environment, whatsoever it is. The thing is, what is it that we know? We know about our spaces, we know about the things that are there, we know what are the different things that can happen over there. So there is some sort of a predictive learning that we have, or some sort of a predictive understanding that we have. What are the different things that can happen in the particular space that we are in? Okay, world models, in my understanding, and very naively saying it, is like a mental model which allows us to operate in an environment that we live in. Right? World models. Why world models are important? World models are important both for humans and the machines. Humans, it comes very naturally. I mean, though it's a process of evolution as well. If you look at a small child, what are they trying to do? They would, like, you give them a toy, they would try to look at the shape of it, the perception of the color develops, and then they keep touching to understand the space, crawl along. So the understanding of the depth, height, also the fear aspect of it, like, okay, what is the height that we can jump from reliably? All of these things come develop in our understanding, right? And so those world models evolve in a human mind also as we progress, right? So this, we want similar kind of mental models or world models for a machine as well, that can do the tasks like a human can do with similar intelligence. So that is my understanding of world models. Once again, what does world models allow to do? Like, you think from this way: as a child progresses and is able to function, they are able to do more tasks in the normal life. A small child is not able to. We can't really ask a small child, say, okay, you are a biological being, you are smart, do all of these things. No, they can't do it because they don't really have an understanding of the world, right? They have to build a world model.
Yeah.
Similarly, for the machines, we need to build a world model where they can understand the world, and they can say, okay, after a reasonable age, are they able to do those tasks or understand those tasks, or can, with minimal information or instruction, we are able to execute those tasks?
Yeah, got it. So the follow-up question, when I was reading how OpenAI came through, Ilya said that he was earlier into robotics, but because it had a data problem and so training problem, he decided LLM is first easier to solve, or not easier, but he decided this is better to solve, and then when there's data problem solved. So how do you train the world models?
So that's a great point of view, actually. So yes, OpenAI was trying to solve the robotics problem first, which is like at the the crux of all of it, right? And so one of the thing in general, and if you talk to, like, so in robotics there are also two schools of thoughts. One is where you can provide structured information and all sorts of. So one would be more, if I have to put it naively once again, one side would be more of, say, non-learning side of robotics. The other is learning into robotics. Use more data, try to give it more experiences and all that stuff. The data problem in robotics is real. And partly because not the it's infeasible to get it. It's just that it's expensive to get it. And the other problem is, like, the people who want data are different from the people who collect data. And so that becomes a big problem. Language, there's a lot of internet is flooded with the text data. You can write your web scrapers, download the data, train the machine. So the LLMs, the success of LLMs once again gives a vector that, hey, given a sufficient amount of data that we have, we can train our machine learning models, or we can train a computer to predict, like, the to understand the structure in the language very nicely, such that it can help us in the basic tasks of writing a document, or rewriting, or rephrasing something, or be able to tell us about certain things that we are interested in. It's not the end of the road. It's basically said that, see, here's a vector over here. By using large amount of language data and big neural networks, we are able to reduce a structure in languages and be able to do the tasks that we were not able to.
Yeah.
Maybe if we provide this large amount of data for vision, for sound, or from a robotics perspective, with manipulation and all those things, maybe we will be able to achieve similar level of outputs for robotics, for vision, for audio as well.
But the training of LLM and training of world models would be very largely different, right? Which is what I was asking on the JEPA part also. That, like, the way we've done RL on LLMs is not how we'll do training on JEPA, right?
So first, like, there are challenges from engineering perspective also. Okay, there are so many terms over here. Let's nuance them first. What is RL and what is JEPA? Okay, and then the training of the world models in contrast to how we train LLMs or the models using language. Language, as I said in the beginning, it's a very compressed form of the communication. It's very structured. And the way it has been defined, like it's less of an engineering chaos. Like, I mean, think of it this way. Before you even train something, you have to store the data somewhere. Now, how much does a text cost versus how much does an image or a video cost? Okay. There's a large difference, right? So before we even like, yes, we've been building resources and all those things to train these kind of models. First is acquiring this kind of large high quality data is a serious nightmare. I mean, if somebody can solve this data problem, how to acquire a good high quality data, that's a big win. Then second thing comes into the engineering efforts, like how do you like make sure before your training you are able to store and access all of that diverse data that you have. I mean, we had a panoptic studio at Carnegie Mellon back in the days. It had like 500 cameras, just VGA cameras. VGA is 600 cross 480 cameras, 600 cross 480 resolutions. Okay, not too high, but 1 minute of that panoptic studio would generate a terabyte of data. Now, if you think of it this simple way, if I just take like let's say the cameras set up in along on the road basically, right? And if I take their feed along the day, storing and training, how much data are we talking about over here? This is like beyond petabytes also. Many petabytes. I don't know how much data would it be, but it's humongously large. Where do we keep all of that data? We can't really keep it in one system because that slows it down from an engineering perspective. If we keep it in a distributed way, how do we keep it? So there are not just challenges from the mathematical modeling side of it, but there are interesting challenges from engineering point of view, especially like what do you do when how to store this kind of data, how do you access this kind of data, and then how do you like learn from this data. Now there are interesting things which happen, and this is where JEPA comes into very nicely. So one naive way, okay, is you can say prediction is one way to do the learning because it's the prediction that's connected to intelligence, right? What you do, like given you're standing at time t, you know how things would be after next few seconds, right? That's your ability to predict, right? So initial version of intelligence, what Yalakun and colleagues they were trying to do was they would say that, hey, what we're gonna do is we're gonna train model to predict the frames of a video. Meaning, if I have to say it naively, if I give you one frame, right, at time t is equal to 0, you have a machinery which should be able to tell me what would happen at time t is equal to 1. Okay, and so on. You can make it longer also. Now, why is it that this thing was hard to model? Pixels, by their very behavior, are untamed. The thing which I'm saying is, think of it this way. You have a camera installed on a road, right? And let's say you're in Pittsburgh where clouds keep moving around. Okay. You're looking at time t and there's a cloud which passes over. Technically, on the road, nothing changed in from our understanding, from an intelligence perspective. But from the pixel perspective, the whole lighting has changed, right? So even though we don't really see anything changing on the road, like on the empty road, right? From a pixel perspective, a lot of things changed, right? So what Jan and colleagues realized is that maybe it's not right to do prediction in the pixel spaces to predict next video frame. What we should be predicting is some latent space of that frame, which is agnostic to some of the nuances or nuisances in the environment that we don't really care about. Okay. Yes, cloud passing from the top is an example, is a very simple example which I am taking, right? It's an important thing. Maybe we need to model it. But for most of the tasks, we don't really even need to think about it, right?
Right.
So can we bypass all of those nuisances by coming to a latent space, like a compressed representation of that frame, and say that let's do prediction in this compressed space, which doesn't have nuisances like those, which are hard to model. So from predicting the next frame in pixels to predicting the embedding can say is as a compressed latent representation of the frame, right? So that's where JEPA comes in for predicting the embedding of the next frame or next few frames. So I think it's joint embedding prediction something, right? This is JEPA, okay? We made a point about JEPA, and you can see the complexity of how is it coming from. One more thing which you said, the training part. हाँ 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 तो अब ट्रेनिंग पे आ जाते हैं अभी सपोज कर लेते हैं कि सारा इंजीनियरिंग वाला पार्ट हो चुका है सो देन योर पॉइंट वाज अबाउट like let's say in the reinforcement learning scenarios that we took.
To world models, not just the new architecture. I'm saying just in general, since you're also doing something on your own with the world model, I'm asking you how difficult is the training?
So here is a thing, and it would depend on what is the variety. Like as you meant the thing more diverse and more rich, the training is going to become more and more difficult. So let's say if you just say that your understanding of the world is limited to the room that you live in, that's totally fine.
Is it possible? Is the first part like training world models? Or maybe you are saying, can give me context. Like, let's say if we are doing weather prediction, hypothetically, how the training would be very different from fashion and virtual training would be very different from self-driving cars and traffic, right? So you're asking me to say, be specific about the context in which training is being spoken about right now.
Yeah, so I mean, I'll have to zoom it out a bit. Can we zoom it out a bit and then go into the details? So first part, let me try to see I understand. What you are saying is, do I need one large model which can do all of these things? I have a bunch of small models which do different tasks, and but I know the connectivity between those small models.
Yeah, the chart you started with. Until now, robotics was okay. If I want laundry, one robot. If I want dishwasher, second robot, whatever example.
Hmm.
Then you said should be like a humanoid which can do everything and has context across the house. I'm still, that's where I'm coming from. When we do world models, like LLMs that have context of many things, and you can repurpose them as per how you want them to fine tune for specific tasks. Is training of world models possible in a similar way?
So the way I would say is there are certain things which are basic essentials. Or once again, let me take a human analogy over here. Okay. There are certain things which are essentials and that remains in your active memory all the time. And there are certain things which I would say you have a hard drive somewhere, you download it into your cache, right? Such that you are able to perform that task. So my understanding would be like, let's say you have world models. So there are certain set of things which you would want to be activated almost all the time, which is like, let's say navigation or understanding about the people in the environment so that or the objects and obstacles in the environment. Okay, but then there would be task specific things which you would know, as you said, context, which when needed can be brought to your like active memory or to your cache uh, quickly. So I think yes, you are right in the sense that we don't really need to say that okay, there is one thing which is doing like we don't really have to do all the learning in one go. In my understanding, in my limited understanding, what we should be doing is rather than saying that hey, I know this is how to solve this problem, we should take an evolutionary approach like a human child would do. In the beginning, the learning might be slow, but over the period of time, because of this continual learning, the model will be able to learn much more things than a human define. So once again, instead of us defining the task, we say let the machine learn about the basic tasks and let it interact with the environment for a few months or a few years. The intelligence that it will acquire would be much more than something that we have designed over a period of time. Does that make sense?
Yeah, it makes sense. But I'm also sensing then you're saying it's we very early. We've yet not figured out how to do it.
We haven't figured it out totally. So I would say uh, we are there are many problems actually. One, we have not even figured out what exactly is it that we want from the world models, our expectation of the world models. So the impact of it is we don't really know how to evaluate the success of world models.
Do we at least know what problems we wanted to solve?
There is no consensus in my understanding. Everyone has their own version.
And some
Okay.
of them, can it be justified, like if you're doing for a filmmaking? But like making a human team making a film could cost, let's say, 10 million. World models designing a film can take 20 million. Then why are still people working on it if that is it justified the extra 10 million you'd put just so that you can prove that world models can make a film?
So it's a proof of concept, I would say. I mean, so you made a movie, like let's say one movie in 10 million, right? And let's say you have a world model which made its first movie in 20 million. You demonstrated that in at least in 20 million, you can make one. Now the goal would be, can you optimize on that?
Got it. Got it.
It's a
I
proof of concept.
I hear you. Got it. And it's always the last 1 to 10% that's the most difficult, even in self-driving cars, right? And that's why they've not become a reality, especially in India. Everyone knows how to drive on good lanes, like you were telling me on the call. The minute you get into India, even humans can't drive it correctly.
Oh, here is the thing with self-driving cars. Let's once again zoom it out. So Pittsburgh is where the self-driving craze began from in 1980s. Okay, uh, the understanding or the rationale. Roads are structured in US. Roads are structured. There are like speed limit and like, okay, which lane leads to this, where do you have to turn, and all of those things. They are pretty well marked.
And
So
everyone follows the rules, you're saying.
everyone follows the rule. Everyone follows the rule. That's true. Most of the people follows it. Now the question that would come is, okay, I need to know the structure in this environment, and I don't really need to drive at say 100 or something like that. Even if I'm driving like somewhat reasonably, I should be fine. As long as I can keep my distance from the remaining cars, I need to just drive in that particular lane. Yes, there are challenges due to pedestrians and all those things. Most of the days, that's the scenario. And if you take a data driven approach, that is what you see most of the days. There isn't anything interesting happening. The accidents that happen or the interesting thing that happen are just a very small percentage, but those are the things that we care about, right?
The anomaly.
Like these are the anomalies, you can say. Those anomalies doesn't really exist. So yes, you can work it out on most of the days, but when it comes a bad day, then it doesn't really know. So one funny experiment I usually, this is I joke about. So let's say when the self-driving cars become a reality, what I'm gonna do is I'm gonna stand in front of a traffic light, like just along the footpath, right? So the like, let's say I'm standing over here, the car is over here, right? I'll just pretend to take a step ahead. So it will see there's a pedestrian will not move. And so all the cars are gonna stop because they see that there is a human which is going to stop over here. Gonna- So but if you actually have a real intelligence, there's a person looking at me and saying that what is it my intention or have to make a cross. See that gap over here? Like you can bring the entire intelligence system to halt by just the simple action. Like the complete road can come on a halt by you standing on a traffic light and just pretending like just take a small one step over there.
Yeah. While a human will be like, this guy's not going to cross, let's go.
This guy's, I mean, or at least you will watch into their eyes, okay, and say, okay, even if they're crossing and whatever is it, like this guy is making fun or something like that. So the intelligence has to evolve to that particular level. Now, coming to the Indian scenario, as you mentioned, rightly mentioned, it's completely unstructured in that sense. And it's true for a lot of developing countries in South Asia and Southeast Asia as well. So the question would be, can you take your car which was designed or which is learned only to do things on a good day, do things when you don't even know what to do? So I think that's where the real intelligence come into picture. We are quite far away from that, in my understanding, for sure.
Yeah, I understand. And your understanding is my most accurate understanding because you've seen it through, right? Through your PhD, through that environment in Carnegie Mellon. So I'm
Yeah.
leaning on to what you're saying. I would just like to take the last segment where I personally want to understand your opinion on or your experience first spending time in the robotics space in Carnegie Mellon. But what did you learn? Also, who really inspired you to pick this subject and dive deeper? Like those personal nuances, I just want to, because maybe there is someone watching, wanting to be interested in this space, and you have already kind of from India gone there, explored it, and come back to India. So, I mean, I just want to understand how that journey evolved and who really inspires you.
So from the beginning, like I don't know how to a lot of things happened also. And let's say this thing. I was trying to do more of statistical signal processing stuff in my undergrad. I didn't know that these have implication in robotics also in India. And but some of the work which I did, there were people out there who thought might be interesting.
Was there an aspiration to get to Carnegie Mellon and say, okay, that's where I want to do robotics because of the history of that place? Like that was that intent very strong from the early days itself of your studies?
It has happened over a period of time actually. Some things happened, some things I learned. So, for example, I went there first in 2010 as an undergraduate intern. Okay. I know certain things about statistical signal processing. I know some things about Kalman filter. And then there was a group over there which was working which was trying to do three robot localization using Kalman filter. And the thing which they did was change in the sensor and asked me would you be willing to experiment on these particular three robots? These were laggards, LAGRs. That was my first introduction to let's say it's like you put a kid in a candy store. Okay. I know, okay, some things about, okay, let's say signal processing part or some mathematics of it, but I haven't actually seen that in action, that the especially for the robotic side of the thing. Okay. So that changed a lot of things for me. And when I returned from my internship, the energy of being in that particular group was something which I was always missing. So uh, after finishing my undergraduate again, uh, I didn't go for a full time position. Took an internship position again at Carnegie Mellon. Yeah, the plan was to do something in once again something in statistical signal processing using a robot. But there was a change in the plan on the last day of when I was to arrive. The faculty over there, he thought he had another project and he put me over there, which was about computer vision. So it was a actual. Now I think in retrospect, it was very interesting. So given you have an object, there's a dog like of robot. Okay, you show an object to that dog, just in once, throw it in the environment. The job of the dog is to bring that object back. Okay. And so it's very fascinating from today's scenario. And I know some of my friends also. I said, I was an undergrad who made this robot worked. Your robots are still stuck just stationary and not able to move also. And this, if you think of it, is a one-shot learning scenario. You just show the object, throw it, it understands. Okay. And so I built the object detection part of it, the vision module of it. Okay. So there are two aspects, that object detection and the manipulation part of it. I built the detection module. And that robot did really well actually. And I got some other opportunities. During the course of my time, I learned about a big chunk of work that were done by pioneers like Chakio Kanade. Okay. Chakio Kanade was at CMU, has done a lot of work in this particular segment. Got and like inspired by the work done by people like Ivan Sutherland. Ivan Sutherland is the founding father of computer graphics. So one of the things which always bothered me, so when I designed or when I worked on that particular robot, right, the first robot which I mentioned in 2011, which was a dog robot, show it an object and fetch it. So I was on the field all day to do the testing, to build and to see what's really happening. And one other thing which I felt was, and this is not really scalable, we need something which allows us to get this kind of rich rate.
Got it. Got it. Okay. Got it. Thank you, Ayush. On this note, we have to wrap up over time. I also don't want to take a lot more of your time, but thank you so much. I think we have a lot more to learn. If there are follow up questions from the audience, I may have to get you again for 15, 20 minutes to answer those. But thank you so much.